question session.
We are live on YouTube now, but I just sent a link to Slack, so it will take 1 minute for participants to join.
Maybe we can even wait 2-3 minutes to let everyone.
Yeah. So I think we can start.
Okay. Good morning, everyone. My name is Marharyta Aleksandrova. Today I will be presenting you the topic Fundamentals of Causal Learning. I will start my presentation with a brief introduction of myself, where I am working, what I am working on. So currently I am working as a postdoc at the University of Luxembourg. Luxembourg is a small country in between Belgium, France, and Germany. University is also a small one and rather a new one. It has less than 20 years old. It has a couple of campuses around the country. I am situated on the south here. This is the photo of the campus where I work. It was constructed on the place where before a steel factory was placed. So it has very interesting architecture and design. You can see some artifacts here on the photo. Before joining University of Luxembourg, I did my PhD on the joint supervision program with two universities, National Technical University of Ukraine, Igor Sikorsky Kiev Polytechnic Institute. This photo that you can see now, probably many participants from Ukraine have heard about it. And the second institution was University of Lorraine. This is a university in France that is situated in a beautiful city of Nancy with the photo that you can see here. This is all with the introduction. Now we will move to motivation behind the topic that I will be presenting. So probably everyone have already heard that correlation doesn't imply causation. And there are a lot of examples that show us that this is indeed the case. For example, from this website, you can find a lot of funny examples that show correlation of the things that are at all not related. For example, here we have the two graphs, two time series. The first one shows the time series of two variables. The first one is worldwide non-commercial space launches and the number of sociology doctorates awarded in US. We can see that these two time series follow each other very tightly. So the correlation will be very high. However, our common sense says that there should be no any relationship between these two variables. Another example is presented on the second graph, and it shows the relationship between the divorce rate in Maine with the red line and the per capita consumption of the margarine with the black line. Again, we can see a very tight relationship between these two variables that will be reflected in a very high correlation. However, this correlation, if interpreted without common sense, will be very misleading and will lead us to wrong results. So the question of correlation and causation and the relationship between them is very important, and especially now when we're trying to automate as much as possible the data analysis. We are also trying to use data analytical techniques to take crucial decisions, whether to hire a person or not, whether to adopt some governmental policy or not. We have to keep this question in mind and know what are the problems that can occur in this situation. So what is cause in general? This question was asked long back by philosophers, and a common answer is cause is something, change in which implies the change in the effect. So we have some fundamental ideas here that we have to be able to manipulate the cause, and there should be a visible change in the effect. From the data, we can observe some correlated changes. However, they can be explained in different ways. For example, here we have three types of relationship, in which case we can observe relationship or correlation between two variables, x and y. The first case, x is causing y. The second case, y is causing x. And the first case, we have a common confounder, that is variable z. And this is the common cause of both x and y. Having just the data alone will not allow us to distinguish between these two cases. So is there at all any way to distinguish between correlation and causation? Well, people have been trying to work on it, and there are now a couple of a number of methods that were proposed. And the golden standard to work on causal relationships is known as controlled experiments. This is essentially experiments that were designed by people, and during these experiments, we randomly select some people who will be allocated one value of cost, and another people who will get another value of the causal variable. And by controlling all other possible confounders that are they're represented with the variable z here, we can say that all no visible relationship or correlations between x and y can be only explained by the causal relationship between them. Controlled experiments are expensive. You can imagine in many cases we have to construct an experiment by itself. We might need authorization from the government, from the authorities. It can be also expensive to gather people if it concerns the people, or for example, prepare the task lab, perform the experiment, and so on. So it is not always a good idea. Also, it is not always possible to run a controlled experiment. For example, if we are talking about such things as a relationship between smoking on the health, it is just impossible to ask some people to smoke only because we want to test this assumption. This is non-ethical. This might impact their daily life. So controlled experiments are not always possible. The question then arises, are there any other ways to identify causal relationships from the data itself without running the experiment? And this is what we will talk about in this course. Now I would like to talk about a bit about historical perspective. For those of you who attended the keynote presentation on Monday, you already have an idea what is causal learning, how did it occur. But there are some things that were not mentioned, and I would like to highlight them here. Causal questions, in fact, they are not new, and people have been working at least on these questions at least for last 100 years. And in fact, causal questions are the basic questions that are asked in social sciences, such as economics, sociology, or biomedical trials. All these specialists in their daily life, in their daily research, they are concerned about causal questions. For example, economists, they want to know what will be the effect of a particular economical policy. Sociologists might study some trends in the society and how they can be shaped in a particular direction. Or medical practitioners, they would want to know how a particular drug can affect the recovery from a disease. So all their research is about finding causal relationships. And they have already developed quite a number of methods to do that. Now we see the trend that causal learning is being adopted by machine learning practitioners, and that is expected and a very good move. However, we should not forget that a lot of work has already been done, and we don't need to reinvent the wheel once again. We should probably use the techniques that are already available. In most of the techniques that were developed in social sciences domain, they require understanding of the domain knowledge. So they have some limitations. However, as was already said during the keynote presentation, in order to distinguish between causal relationship and correlation, we always have to do some assignment, some assumptions. There is no free lunch. So it might be a good idea to learn about these methods and see how we can adopt them in our practical tasks, and further develop and try to see how far we can push the boundaries, and what are in general theoretical possible assumptions that can allow us to do some causal inference. So in this work, this presentation, I would like to focus and introduce to you the methods that have already been developed in social sciences. So for those of you who come probably from economical domains, or have studied causal inference in social science related disciplines, a lot of things might be not new. However, for me, being a practitioner in computer science, a lot of these things were a discovery, because we don't learn them in our university programs, and many times we end up reinventing the things that already exist. So in this talk, I would like to I will have 4 parts of the presentation. First, I will start with the formalization of the problem of causal inference. What is the main terminology? How we define the causal relationships, and how we define the process under which we can distinguish between correlation and causation. Next, I want to talk about causal graphs or structural causal models. These are the models that are widely used, not only in social sciences, but also currently by those practitioners who try to develop causal learning within the frame of machine learning. This is an instrument that is very useful for not only understanding the domain knowledge and grouping it all together, but also to make some inference and design properly an experiment in such a way that your discovered relationship will be causal. In the third part, I want to present some common experimental designs for causal learning. These are those designs that were developed within the framework of social sciences, and that can be, in fact, in many cases adopted by us, by data science practitioners. And I will conclude this presentation with the discussion of the relationship between causal learning and current machine learning, what is currently being done, what researchers are working on, and how we can benefit from the causal learning theory that is already developed, and how we can develop it in the frame of machine learning. Okay, so we'll start with the first part, formalization. Here we'll talk about what is causal effect, what are causal assumptions. Essentially, these are the conditions under which we can talk about distinguishing between correlation and causation, and then we'll talk about such notion as confounders. So, what are causal effects? Imagine that we have such statement: I took ibuprofen and my headache is gone, therefore the medicine worked. Is it correct causal statement? No, it is not, because this statement doesn't imply that it was ibuprofen that caused any change in the health state of the patient. Maybe there was something else that implied this. Maybe just the patient had some good rest. So to be able to identify the cause, we need to ask ourselves, what would have happened otherwise? With the same patient, under the same conditions, preferably in the same day, what would have happened if the patient didn't take this medicine? In this case, we would have 2 possible outcomes. Outcome 1, related to the first situation, and then outcome 2, related to the second situation. And in case we see any difference in between the 2 outcomes, only in this case we can talk about causal effect, and we can also measure it by applying some functions to this outcome, for example, taking a difference or the ratio or something like that. So in ideal situation, to define some causal effects, what should happen? We should have some population, original population, and we should have two realities, two hypothetical realities with exactly the same population. For in one reality, we should assign them to have some value of the causal variable that is also known as treatment. We will be using throughout this presentation the letter A to refer to the treatment. Treatment is the same as the causal variable, just particular value of the causal variable. And another hypothetical world where we have exactly the same people under exactly the same situation, which were not assigned the treatment. It means that they had a different value of this causal variable. Then we can observe potential outcomes of our of the variable of our interest, that is the outcome variable y, under the first condition when the treatment was applied, and under another condition when the treatment was not applied. And then we can compare these two values, as it was said before. So we can compare them. And this is known as individual treatment effect, or the causal effect on a particular individual. In other case, we can, if we are working with a group of subjects, we can take the mean value of all individual treatment effects, and then we will get an average treatment effect that will allow us to better estimate the causal effect, because like this we can control for some other cases, like some people, for example, are more healthy, so or they will recover faster if we are talking about some problems with the health. And the fundamental problem of causal inference is that it is impossible to have these two situations at the same time. We just cannot, almost in any case, have the same group of people or the same person being assigned different treatments. Even if we assign, for example, on the first day, we assign the treatment to people, on the other day, we don't do it, still it's already a different world. We change from day 1 to day 2, so something might have changed. They got older, or a lot of things that can happen. This is already not the same situation. So we can observe only one outcome. Assume that in this case, we observe the case when the treatment was assigned. The other case can never be observed, and it is known as counterfactual. And then fundamental problem of causal inference tells us that we can never observe at the same time the state that is observed, that we can measure, and another one that is counterfactual, that is imaginary. So how can we identify causal relationship in this case? Well, we can try slightly different situation. Assume that we again have the same population as in the beginning. The whole population can be population of people, or if we're doing some experiments with some physical structures, so we have the same group of subjects on which we want to test the causal relationship, and then we can split them into two groups. And one group, the first group, will be assigned the treatment, and another group will have no the treatment. And in this situation, we can observe at the same time the two values, that is the value under the treatment and the value under the absence of treatment. However, they might not be the same. in the sense that there might be some bias in the way the groups were selected. Like for example, if we're talking about recovery from the disease, for example, people here were those who were younger, so they will recover faster. Or people here were those who were healthier, so they didn't need the treatment, and again, they will recover faster. So we can have some covariates, X, that will have additional relationship, additional effect on the cause variable, and will not allow us to estimate the supposed causal relationship. In this case, the randomized experiments help us because we assign the treatment randomly. It means that the whole this population is split on two parts, on those who get the treatment and those who don't get the treatment, absolutely randomly. So there should be no other variables, confounders that can impact the choice for whom the treatment is assigned. So we try to control for this part. In this case, we can assume that the observed outcomes, that are these conditional outcomes, the things that we observe, can be equal to true causal relationships. However, it is not always the case. So in general, the treatment effect might not be equal to the difference in between the observed variables. However, we can overcome this under some assumptions, and we will discuss them now. So what are the causal assumptions under which we can talk about causal inference? They are generally known as identifiability assumptions, and in many cases that they cannot be tested. So we need to have some domain knowledge, some understanding, and just do some assumptions to be able to derive some causal relationship. And these are the assumptions that are made on the outcome variable, that is something that we want to measure the variable on the effect on which we want to measure. For example, the speed of recovery, assumptions made on treatment, that is the causal variable, the variable that we want to manipulate, and assumption made on covariates, that is the set of variables that can impact the treatment and the outcome at the same time. So let's discuss these causal assumptions. There are 4 of them. First of them is known as SUTVA, or stable unit treatment value assumption. And it says that treatment should be the assignment of the treatment doesn't impact the outcome of the another person. Let's imagine a situation, for example, when again we're talking about the recovery of 2 people, and the 2 people were assigned to have the treatment. So we have for them the treatment is equal to 1, and they are just talking in between each other and exchanging their ideas and how do they feel. And one person can be very happy that the treatment is working, can be sharing this positive mindset with another person, and another person will just have his mood higher, or maybe will get some belief that the things will go better, and this can affect the recovery rate of the second person. And then in this case, essentially, the second person will recover not only because of the treatment that was assigned, but also by the support, or they will just believe that I am feeling better because the other person is feeling better. This is the first assumption, and this can be made, this can be controlled for example, if the subjects cannot interact between each other. Another assumption is that there should be another part of this assumption, stable unit treatment value assumption, is that there is only one version of treatment. And it says that at the same time, we are using only one treatment. For example, if we are testing the recovery from the disease, we test only one drug. We don't give 2 drugs simultaneously to the same group of people, because in this case, we will not be able to distinguish which drug effectively led to the recovery. The next assumption is the consistency assumption. And it says that potential outcome is equal to the observed outcome. So this comes again from our graph that we saw before. As we said, we cannot observe counterfactual. So we cannot have the same group of people at the same time being assigned the treatment and not being assigned the treatment. So we split them on 2 groups like this. But we assume that, for example, here we have a treatment, and here we don't have the treatment. This is one part and another part. But we assume that the effect that we see under the absence of the absence of the assignment of the treatment for this group essentially corresponds to the effect, or somehow represents the effect of the absence of treatment that we would have observed with the first group, haven't they not been assigned to have a treatment. The next assumption, very important assumption, is ignorability. Essentially says that there are no unmeasured confounders. And what it means, as we discussed, there can be some other variables, confounders, that can affect the assignment of the treatment, like those people who are less healthy have higher probability to be assigned the drug. And we assume that all such confounders can be measured. Otherwise, in case they are measured, we can do something in our analysis. We can control for this variable and in this way take into account the relationship. However, if there is some confounders that we cannot think about and we cannot measure, there is no way for us to correct for this possible relationship and then distinguish between the true causal relationship and the relationship that can be caused by the common confounder. So we assume this as ignorability, and you will see in the following that this is the common basic assumption of many causal learning methods. And the last one is the positivity assumption, and it says that the treatment is assigned in non-deterministic way. And why do we need this? Because if the treatment is assigned in deterministic way, for example, all people who are elder than 60 years, for example, all get the treatment. So all those people who are above 60, they get the treatment. Then there is no way for us to measure what would have happened with these people, with the same people, haven't they not been assigned the treatment. So there is no way we can use this information, and this is just useless for us. So let's see what happens if we take into account this assumption. In reality, we don't observe the treatment effect, but we can observe some conditional probabilities. For example, we can observe the expected value of the outcome variable under a particular treatment, the particular value of treatment. In our examples, it was 1 or 0. And for a particular subgroup of people that is also confounding group. This is what we can observe in reality, both in the experimental data set and in natural experiments, that is the observed data that was not prepared as the experiment. Now, if we if we think about the consistency assumption, that is potential outcome is equal to the observed outcome, then we can replace this observed outcome with the potential outcome. That is what would have happened in reality, have these people been assigned a particular value of treatment. So in the hypothetical world. So we'll represent it like this. And this corresponds to the potential outcome. From the observed outcome that is here, we're now going to the potential outcome for the same value of treatment and for the same confounding group. And the final step, if we assume the if we assume that the treatment is assigned independently, that is, this part is not important, then we can drop this and we can get potential outcome for a particular group of people, for a particular confounding group. That is, from the observed data, we have come to the definition of the treatment effect. That is how we can argue that, that under these assumptions, from the observed data, we can derive the treatment effect itself. We have been mentioning a couple of times the confounders and how they're important essentially in our models. We'll be always working with some outcome variable, with some treatment, the effect of which we want to evaluate, and some confounders that are the variables that can potentially prevent us from estimating correctly this effect of the treatment on the outcome variable. So let's discuss a bit more the confounders. Confounders essentially are defined as by definition, this is the set of variables that can affect at the same time the treatment and the effect, as it is represented on this graph. And as it was said before, why the controlled experiments are good? Because we can control for confounders and for both observed and unobserved confounders, because we can randomly split our group onto our population onto two groups, those who will be assigned the particular value treatment and those who will not be. However, there is also a way to solve this problem for the case of observational data, and that is the conditioning. The conditioning essentially means that we do separate analysis for different value of our confounders. For example, for a gender, we can do a different analysis for the case when we work with males. We will have one value of causal effect, and we can do the separate analysis for the case when there are the gender is female, and we'll get another value of the treatment. And in this case, when we do this control, so that is we split on two groups, there is no way the gender can affect the assignment of the treatment, because in the group of all males, there are only males. So there is no way the gender can affect somehow our model. This is all about the terminology that we'll be using, and now we will talk about causal graphs. So we will start with the definition. What are causal graphs? We'll discuss a couple of examples of the causal graphs. Then we will talk about how causal graphs are related with the probability distributions. After that, we will discuss the paths in the causal graphs and how they can show us information about the association between the variables. And finally, we will talk about how we can achieve conditional independence using all this knowledge that we gained above. Essentially, causal graphs, they will allow us to estimate what are possible confounders, as we discussed on the previous slide, so we can have our treatment and our outcome, and we can have some possible confounders. And this is where the problem comes from, because our observational data in the observational data from this statistics that we can calculate, we will get information both about this relationship and this relationship. So we will not be able to distinguish between them. However, when we can condition, that is split condition on these confounders, this relationship will go away, and all that we observe in the data represents the causal relationship. So the graphs will essentially allow us to identify for a particular problem what are the set of the confounders and how we can control for these confounders to get the proper causal relationships. Okay, so start with causal graphs. As it was already said, so this is causal graphs are a great tool for the analysis and inference of causal relationship and understanding of what can happen in the system. They encode assumptions about relationship between different variables. So from causal graphs, we can identify whether some variables are independent, dependent, or conditionally independent. We can use them to simplify our joint distribution. So what is causal graph? Essentially, the definition is any directed acyclic graph can be viewed as a causal graph or causal structural model. So for example, if we have the two nodes, there is a link between them, and if it is directional, this can be a causal graph. However, when we have nodes with unidirectional link, or there are some loops in the graph, these types of graphs cannot be causal graphs. So these types of graphs will not work. Now let's talk a little bit about terminology. Assume that we have the following directed acyclic graph. So we have four variables, W, Z, B, and A. And the way the relationships are represented in this graph is W has a causal impact on Z. Z has a causal relationship with B. Z also causally affects A, and then A has a causal effect on B. Every variable in this case is known as node, is referred to as node. Then following the edges, we have the directed paths. And for example, here on this graph, we have two directed paths between the nodes. Between the nodes W and B, we have two directed paths. One goes W, Z, B, and another one goes from W to Z, then to A, and then to B. So these are two possible paths in between W and B. The parents are the set of nodes that has causal effect on a particular node. So for example, for the node Z, it has only one parent, W. And node B, for example, has two parents that are Z and A. Then the inverse part of the relationship is a child. So node B is a child for Z and A, and node A is a child for the node C. And we can have ancestors and descendants if we move a couple of hops before following this causal relationships link. Now let's talk about what probabilistic information can be encoded in causal graphs. We'll start with the first example. So we have the following graph. We have the node A that has causal effect on B. Then we have the node D that has a causal effect on A. And there is node C that is not connected to any other node, so there is no causal relationship between C and all other nodes. So what can we derive from this graph? For example, let us think about the probability distribution of C given all other variables, A, B, and D. From this graph, we see that there are absolutely no connections between C and all the other nodes. So C is independent on A, B, and D. That can be written in such a way that conditional probability of C given A, B, and D is essentially equal to the probability of C. Let's move to the next node. Let's now talk about node B. So what will be the probability of the B given A, C, and D? We see that D is not related to C, and it has only one relationship with A. Even though the node D affects the node B through A, however, all the information that flows from D to B goes through A. That means that as soon as we know a particular value of A, the knowledge about D doesn't give us any new information. So from this, we can say that this value will be equal of the probability of B given A. That node B depends only on A, and that means that the node B is conditionally independent on the node C, on the other nodes C and D, given the value of A. So from the graph, we can derive some probability relationships between these variables. The next thing that we can derive is that the following. Let's think about probability of B given D. So again, if we look at the graph, there is a path from D to B. So there is a relationship between them, and it means that they are dependent, and essentially that this conditional probability is not equal to the marginal probability. That is, probability of B is not the same as the probability of B given D. These two nodes are dependent. And the last thing, let's discuss about node D. So what will be the probability of D given A, B, and C? Again, from the graph, I will change the color. We see that the only relationship between D and A and all of the nodes is the relationship between D and A. Even though D is related to B, however, B has no impact on the node D. There is no way the change in B can impact the value of D. And of course, there is no connection with the node C. So we can write that this conditional probability is essentially equal to probability of D given A. Okay, let's consider a couple of other examples. So now we will discuss a lot of quite a number of theory to understand how causal graphs can be interpreted However, this will be used later to identify the possible set of co-founders. So let's have a look on another graph. Now we have the node A, node D, node B, and node C. And we know that D affects A. There's a causal relationship. D has a causal relationship on B, and D has a causal relationship on C. So what we can derive from this graph? Let us think about the probability of A given all other nodes that are B, C, and D. So as before, A has the only link to the node D, and this is the only node that affects the value of A. There is no way the value of B can impact the value of A, no way the value of C can impact the value of A. So this can be just written as a probability of A given D. And it essentially means that A is conditionally independent on B and C given the value of D. So it is conditionally independent of these two nodes. As soon as we know the value of D, the values of B and C cannot give us any more useful information about the value of A. Next, let's think about the probability of D. So what will be the distribution of D given the other nodes? We see that D has a relationship with A and B. And because this is a causal relationship, in fact, from the value of A and from the value of B, we can derive some information about what is the value of D. However, there is no way C can impact the value of D. So this can be written as the probability of D given A and B and D is conditionally independent on the node C, however, under the condition that the B is known, because there is a relationship between B and C. Let's have a look on a slightly different graph. So we have A, node A. It is almost the same as the graph before, node B, node C, node D. The connections stay the same. D has impact on A and B. B has impact on C. However, there is additional link in between A and C. So how will the distributions change? Let's analyze the same distribution. So we have the value of P, the probability of A given the values of B, C, and D. So let's have a look on the graph. Now A is related to the node D and to the node C. So this is the conditional probability of A given the values of C and D. And from this, we can assume that A is conditionally independent on B given C and D. And the final analysis, so let's analyze what will be the probability of D given the values of A, B, and C. So D has a relationship with A and B as before. So it is a probability, conditional probability of D given A and B. Exactly the same value as before. However, now D is conditionally independent on C under the condition that we control for both A and B. So we need to control for both value A and the value B, because the connection between B and C goes through two paths, one path and the other path. And to reach the conditional independence, we have to control for both B and A. Okay, so we discussed what can be inferred, what kind of probabilistic information we can infer from the causal graph. And now let's talk about the decomposition of the joint probability distribution from a given graph. There is a rule in which we can do it. And the rule says the following, that we should start with the roots, that is the nodes that have no parents, and then we proceed down the descendant line and do the analysis. So let's have a look on the graph. We have A here that causes B. We have D here that causes A. And there is a variable C that is not related to all other variables. So we are asking ourselves how we can represent the joint probability distribution, that will be probability of A, B, C, and D. So the first thing that we should do, start with the roots, the nodes that have no parents. We have two roots, C and D. So we can start, and then we have to follow the descendant line. Let's start with the node C. So we can write the probability of C. Now we need to follow the descendant line for this node. However, this node is not related to any other node. So we can just stop here. Next is the node D. So we write the probability of D. And now we need to follow the descendant line. So the descendant line from D, we have only one descendant that is A, one child that is A. So we have to add the probability of D given A. And now we have to continue the descendant line, and it will be the probability of B given. Oops. Sorry, there is a mistake. Slight correction. So we have started with the probability of node D, and now we follow the descendant line. So the next node that we are going to process is the node A. So we need to add the probability of A given D. That is, we already worked with the node D, and now what additional information we can get from A. And then we again continue with the descendant line. Node A has the child B. So we have to add the probability of B given A. So this is how we can obtain the decomposition of the joint probability distribution from a particular graph. Let's have a look on a couple of other examples. So another graph, we have the nodes A, node B, node C, node D, causal link between A and D, D causes B, and B causes C. Now, what we can say about the joint probability distribution, that is, what is the probability of all the variables A, B, C, D, and how we can decompose it. Again, we have to start with roots, and in this case, we have only one root, that is D, so we'll start with the probability of D. Then we proceed with the children. The first child is A, so we need to add the probability of A given D. The second child is B, so we have to add the probability of B given D. And when, in this case, we finished with the children of D, next we move to the children of the next node. So the node A had no children, so we stop here. However, node B has one child, that is C, and we have to add the probability of C given B. This will be a decomposition for this graph. And one more example, very similar example. So we have almost the same structure. We have node A, we have node B, we have node C, the same relationship with the node D. However, we added one more link in this case, that is A is now also causally affecting the node C. So what will be the distribution, probability distribution in this case? So what is the value of joint probability distribution A, B, C, and D? Again, we start with the roots, that is the node D. We add the probability of the node D. Then we start to process the children. The first children is node A, so we add the probability of A given D. The next child is B, so we add the probability of B given D. And now we follow the descendant line. A and B have the same child, C, so we are adding probability of C. However, now C depends both on A and B. So we have to write the probability of C given these two variables, A and B. That's all. Now, so as we saw, for every causal graph, we can obtain a particular probability distribution, a particular decomposition of the probability distribution, and we can infer some information about the relationship between the variables. And this information is always unique in the sense for a particular graph, there is a set of pieces of information that you can infer and they stay the same. However, inverse is not always the case. For a particular probability statement, we can have different causal graphs. And this is where the problem of causal inference comes. When we have the observed data, it can be explained by multiple real causal relationships. So we need additional assumptions. And let's have a look on a very simple example. Assume that we know that two variables are related. That is, we know that probability of A and B is not equal to the multiplication of two probabilities, probability of A and probability of B. This is essentially a standard formula that all of you probably know, and it says that these two variables are dependent. However, it can be explained by two causal graphs. The first one is when A causes B, and the other one is when B causes A. The probability decomposition corresponding to the first graph will be the following, that is, probability of A will be, so it will be this one, probability of A multiplied by the probability of B given A. For the second graph, we have this decomposition, that is probability of B multiplied by probability of A given B. And there is no way we can distinguish between them only from the data. However, they correspond to two different graphical models. So we finished with the probability distribution relationship with the causal graph, and now we'll talk about different paths in the causal graph and what kind of association they reveal. We'll consider three types of relationship. First one is fork, known as a fork. And it can be represented like this. For example, we have three variables, A, B, and D. And D has a causal relationship with both A and B. And the name, probably you can guess, comes from the fact that this is visually reminds us a fork. It can be also written in a flat format like this. So we have D, and then we have two arrows going in different directions to A and B. In this case, what can we say about the relationship between the values of A and B? They are definitely associated. Why? Because there is a common cause that will impact both A and B. For example, if the weather is sunny, we have a good mood and the plants are growing good. So in the data, we will have some relationship between these two variables and it will be visible. Next type of path is called a chain, and it looks like this. So we have just a direct flow of causal relationship between variables. For example, here, A has causal impact on D and D has causal impact on B. And again, the relationship between A and B, there is an association that will be visible in the data. For example, A represents the temperature, D can represent whether there is ice on the floor, and B represents the rate of injuries that people fall on the ice. So when the temperature is lower, there is higher probability to have ice, and then there is higher probability of getting injured. So there will be association between A and B present in the data set. And the last type of path is inverted fork. And it is essentially the same as the fork. We have A, B, and D. However, the direction of the relationship is inverted. So now A and B have both causal impact on D. And this can be also represented in a different format, like A causes, in the flat format, it can be written like this. So in this case, A and B are not related to each other. There is no connection between A and B. There is no way B can impact A. There is no way the information can flow from B to A or vice versa. And such situation, the node D in this case is known as a collider. Now let's talk about conditional independence for these different types of paths. So first is the chain. A causes D, D causes B. And the example that I gave on the previous slide, we can assume that A, for example, is the temperature, D is the presence of the ice, and B is the probability of a person falling and getting injured. Now, if we want to, we know that there is a relationship between A and B. However, assume that this is some kind of confounder that we want to answer the question, is there a possibility for us to block this relationship, that is to control for this relationship? And in this case, indeed, it is possible by controlling the value of D. For example, for the value, the D can have two possible values. There is ice, that is yes, yes, and there is no ice, that is no. And when we control, that is when we split on two different groups for the corresponding to the two different values of D, there is no way A can have impact on B. For example, for all those cases when there is no ice, imagine that it is the temperature above 0. So there is no way the temperature can impact the probability of a person being injured. There is no way we can have association between A and B. That is, this relationship, this association is blocked. The same thing when there is ice. For example, the temperature is below 10 and it was raining before. There is no difference if the temperature is -10 or -20. It will not affect the probability of a person being injured. Let's consider another type of path, that is the fork. So we have D that causes both A and B. And again, we ask the same question. So we discussed that there is a relationship between A and B. However, we want to control for this relationship. Is there a way to do it? Let's consider an example. So let D be the variable that says if the weather is shiny or not. Let A represent a mood of the person. For example, it is common that when there is sun, we usually tend to have better mood. And B correspond to the how good the plants are growing. Again, we know that the sunshine is required for the plants to grow properly. When having no condition on D, we can infer from the data set the association between the A and B. So for those days when people have good mood, the plants are also growing faster. And this is caused by the common reason, that is the presence of sunshine. However, if we condition of this variable, that is, we split on two groups, for example, assume that we just say that there is sunshine, so that is the value of D is yes, and there is no sunshine, the value of D is no. For the group of all the cases when there is sunshine, the mood of the person can have absolutely no relationship to the quality of the plant growing, and vice versa. And for the days when there is no sunshine, the same thing happens. So in this way, we can remove the association between A and B, remove the causal, remove the association between A and B. And the final graph that we will consider is the inverted fork. So we have A that causes D, and B that also causes D. To better understand, let's again consider an example. Assume that D, the variable that tells us if there is light in the room or not. And we have two switches, switch A and switch B, and assume that we can turn on the light only in case when both A and B are on. So there is in fact absolutely no relationship between the probability of one switch to be on and the other switch to be on. This can be done randomly by a flip coin. However, so in this case, we don't need to condition on anything. There is no relationship. However, if we do condition on D, then we in fact will open the relationship between A and B. And let's think about it. Indeed, if we condition on D, that is to say that there is light or there is no light. So there is light or there is no light. And if we know that there is light, we know that both A and B should be on. So we know that there is a relationship between A and B. They are both on together. Or if there is no light for the second case, we know that if A is on, then B should be off. Or if B is on, then A should be off, or they have to be off simultaneously. So we sort of open the connection in between A and B. So whenever we are doing control for the type of path that is inverted fork, we should keep in mind that we will open the connection between A and B, and this will can cause additional confounding that we will see later in the lecture. So why do we at all need all this theory? As we said, we want to be able to control for confounders, and we want to know what is the set of variables for a particular graph that will allow us to do this control, to remove all additional causal relationship that is not explained by the relationship between the treatment and an effect. And this notion is known as the D-separation. So a set of nodes induces the D-separation if it induces independence between our two variables that we want to control. That is, when we control for a particular set of nodes, we can guarantee that the two variables are independent. And this here stands for the dependence, so dependent separation. So let us see what is to be done for different types of paths, which we discussed before. The first case is the chain. A causes D, and D causes B. And as we said, if we, in general, will have association between the nodes A and B. However, if we want to remove this association, we just need to control for the value of D. The next case is the fork. Now the node D causes A and B. And again, we discussed that when controlling for D, we can remove the relationship between A and B. So for this type of graph, D will be the set of nodes for which we need to control to remove association, to achieve D-separation between A and B. And finally, for inverted fork, the case when D is caused both by A and B, we don't need to do any controlling. So these two nodes, they are already separated. We don't need to do any additional controlling. And in fact, if we do it, we in fact open a path in between A and B. We open an association. So this something that we should keep in mind. Now, why do we need all this theory? Once again, we come to the problem of the confounders, the problem that doesn't allow us to identify causal relationship just from the observational data. Let's look on the graph. So we have A that causes Y. And if it was only A causing Y, then just from the data set, we can estimate what is the effect on A on Y. But we don't know, maybe there is something else that impacts both A and Y. And in this case, whichever information we have in our data set represents multiple causal relationships, not only the relationship of the treatment on the outcome. But if we now want to control for the confounders, and we can use this theory to achieve this control. For example, we want to remove the additional connection between A and Y that is due to the node X. So we know that we just need to control for it. Or let's consider a different graph when we have again our treatment A, our outcome Y, and we have two additional variables, V and W, and V causes A, V causes W, and then W has a causal relationship on Y. In this case, again, we want to remove additional association between A and Y. And to do that, we can control for the node V or for the node W to achieve this. So this theory that we discussed before will be used to define the rules under which we can achieve independence between A and Y, in the sense that only causal relationship between these two variables is present in our data set. And we will consider only one criteria, that is blocking backdoor paths from treatment to outcome. We'll see how it works. Let's first discuss the types of paths. So we said that there might be a backdoor path, but probably there is also a front door path. So let's have a look on a couple of examples. Again, the graph that we already considered many times. So A, the treatment variable has an effect on Y, that is outcome variable, and there is some confounder X that has the impact on both A and Y. And between A and Y, there are different paths. So one is the path that originates in the point A, and it is known as a front door path, and another one that has A as the arrival point. So this is a front door path. There are two different types of paths in between, every two variable, one front door path whenever we just follow the errors. So we sort of follow the flow, and another type of path where we sometimes go inverse to the errors, and that is known as a backdoor path. In this case, it is the path from A to X and then to Y. Let's consider a different example, so slightly more complicated graph. We have A that causes Z, and Z that causes Y. And then there is a common confounder for A and Y, that is X. Again, we want to see what are the paths in between A and Y. As in the previous case, there is one backdoor path that goes via X, and there is a front door path that goes from A to Z and then from Z to Y. And we never want to block the front door path, because directly or indirectly, they represent the causal relationship between the treatment and the outcome. However, we want to remove the backdoor path that will interfere with our causal relationship present in the data set. And why is it important? We can link it with the ignorability assumption that we discussed in the very beginning of the causal assumptions, that there should be no variables that affect both the treatment and the outcome. So this criteria essentially allows us to make the ignorability assumption hold. So let's see how it works in practice, the backdoor path criteria, how we can use it. The backdoor path criteria looks the same. So a set of variables X is considered to be sufficient to control for confounding if it blocks all backdoor paths from the treatment to outcome, and it does not include any descendant of the treatment, because if it will include any descendant of the treatment, then we will block the relationship between the treatment and the outcome. And there can be multiple ways or multiple sets of variables which can be used for this purpose. So let's have a look on the graph. We have the graph A that causes Y. Then we have Z causes W, also causes A, and W causes Y. So we have our treatment and the outcome. There is the causal relationship that we want to estimate, but there is also a backdoor path going like this. So now we want to block it, and as we said, for this we can do the conditioning. And we can see, or using the types of paths that we discussed before, we can infer what kind of the conditioning can be made. So if we just look on this backdoor path, so this causal effect on V on A and then on W. So this type of connection is known as a fork, and we know for breaking the association between A and W, we need to control for the variable that is in between. So we can control for the variable V. This is the first solution. In this case, we will break the relationship between A and W, so this information cannot be passed through this path to Y anymore. So the backdoor path will be blocked. Another possible option is that we can have a look on it, another part of this path, this part, that is a chain. And again, for a chain, we know In order to block the association between two variables, in this case v and y, we have to control for the thing that is in the middle, that is for the w. And then this will prevent again the information flow from A to Y through this backdoor path. That is, the second possible option is the W that we can control for. And finally, we can control for both V and W. This will essentially give us the same result. So there is also a possible solution, V and W. And like this, again, will block the path. And it is up to the person who is doing analysis to decide which type of blocking is better. Usually people prefer to have less controlling as possible, so to have only one variable, but it might be easier in some application to control for one or for another. But it is useful to understand what are all the possible options, and then to take an appropriate decision what will be the best option to do in a particular case. Let's consider a slightly different example. Again, the backdoor path criterion. So we have again our treatment A that causes our effect Y. And we have a backdoor path. So we have the variable V that causes A and some other variable M. Then this variable M causes W and W causes Y. In this case, let's analyze this path. So we have here we have the first part. It is a fork. Oh no, this is this is a fork. Then we have a chain and again a chain. Excuse me, there is a mistake here. I'll just correct it. So this should be a different type of relationship. This should go like this. Like this. So V causes M, V causes A, W causes M, and W causes Y. So we have a fork, then we have inverted fork on this part, and then again a fork. And as we discussed, whenever we have inverted fork, we have a collider M that essentially blocks the information flow from A to Y. That is, in this case, we don't even need to control for anything. In the original setup, the backdoor path is already blocked. Information cannot be passed from A to Y. So the first possible solution is at the empty set of the variables that needs to be controlled. However, we can try to control for V. There will be no problem. It will just break the association between A and M, or we can control for W that will break association between M and Y, but it will not give us any additional benefits. So another possible ways is to control for V or control for W. However, I will do correction here as well. So the arrow goes in a different direction. This is the same graph. However, in case we do control for M, as we discussed before, we will open a link between V and W. So we will open another backdoor path. And in this case, in order to block this newly opened path, we need to control either for V or for W, or for V and for W at the same time. That is, in case when we control for M, we have to do additional controls. So this is how the causal graphs can be useful for us to understand which variables should be controlled for. Let's have a look on a slightly more complicated example. So we have our treatment A that causes Y. And then we have a set of additional variables. We have W that causes A. It has causal relationship with Z. Z that affects A. And then we have one more confounder, V, that affects both Z and Y. In this case, we have our front door path. We have our front door path between A and Y, which we don't want to block. However, we want to analyze, are there any backdoor paths between A and Y? And in fact, there are, and there are two of them. One goes from A to Z, then from Z to V, and from V to Y. This is the first backdoor path that we want to block. And the type of association, the type of path that we have here, so we see it is the chain and the chain again. So for us, in order to control, we just need to control for something in the middle. It can be Z, it can be V, or it can be both. So Z or V or both at the same time. Another path that we have, backdoor path that we have, goes from A to W, then from W to Z, and then to V and to Y. So what kind of paths we have here? So again, here it is a fork, here it is inverted fork, and here it is again a fork. So essentially, this path is already blocked because on the way there is inverted fork, so the information flow is blocked. However, we can still do control, and we can, for example, control for Z. In this case, however, we will open the connection between W and V, and we need to do additional control. So now, if we want to analyze these two paths together, in the sense we'll try to identify what is the set of variables that we should control for in order to block both backdoor paths. As we discussed in the in order to block the first path, we can use just, for example, the node V. However, and this will be enough because in this case, the second backdoor path stays blocked. However, we can also choose to control for both, like it was here, V and Z. And in this case, we'll open another backdoor path between W and V. We'll open another connection. So we have to do additional controls. If we, in this case, V and Z will be enough because blocking, controlling for Z will open the relation between W and V. However, the further connection will be blocked by the fact that we control V, or we can control Z and W. So if we are controlling Z, then we have to block this connection. So then we can control for V, or for then we can block this backdoor path between W and V. And we additionally have to control for V to block this additional path. However, it is like the solution that was proposed here that we can control for only for Z is not valid because it will block the first path, however, it will open the second path. So this is the case when we have to analyze both solutions simultaneously and choose the solution that is appropriate for controlling all possible backdoor paths. So we discussed the theory of causal graphs, causal graphical models. And in reality, these causal graphs can be very complicated. Like we can have a lot of possible nodes, a lot of possible connections in between them, and assume that this is our treatment and the outcome. And whenever people in social science do their research, in many cases, they try to build this graph that can be quite complicated, and they have to argue that this graph indeed represents all the connections that are possible in the system. However, as it was said before, we always need some assumptions. Without assumptions, there is no way we can infer anything about causal relationship. We only have the correlation. However, using these techniques that we discussed before, we also discussed one of the criterion, that is backdoor path criterion. We can identify the set of variables that should be controlled for, and under this control, we are guaranteed to have in our data set the relationship between the treatment A and the outcome that will represent the causal relationship between these two variables without any interference of causal relationship with other variables. I will stop in this part. It's already time. And the next part we will continue in the next time slot. So I will move to the questions. Alina, if you maybe you could share with me the link where I can access the questions, if you have it close to you.
Sorry?
The questions, I need to search for a link where I can access the questions. If you have it by your side, maybe.
In Slack.
It is in Slack, it is not on Slido.
Yes, in Slack we have link to Slido.
Yes.
Mm-hmm. Did you find it?
Yeah, I'm opening, just a second. Okay, the first question is, what is the relationship between causal graphs and structural equation modeling? So this is essentially the same. In fact, like these types of graphs that we were discussing is directed acyclic graphs, and then can be used to represent causal relationships, and they are useful. So they can be, I was referring them to as causal graphs. And structural equation modeling is essentially using this type of graph to represent the relationship between the variables and try to infer something and infer some information, or for example, do the same analysis as we did in right now, try to identify the possible confounders and control them so that we can guarantee that association that we see in the data set reveals the causal relationship. I will probably also share the screen so that the questions are visible. Second question, example 2, why is D independent on A if D has a causal effect on A? Just a second. If you ask questions with the examples, maybe you can also give me the slide numbers. That will be faster for me to find. Okay, let's see if it is this example. Well, I would ask, could you please reformulate this question? Because if you are talking about this example 2, then there are 2 graphs. And which one do you mean? In example 2, why is D dependent on A if D has a, I think it will be the same. So it is not dependence, but it is, what we are talking here is the probability distribution. So because D causes A, if we have some information about A, that tells us something about D. Because as we discussed, for example, with the the lights and the switches, if we know that the light is on, we can infer what is the position of the switches. That is why there is a relationship between them that can be represented as the conditional probability, but it is not causal dependence. Move to the next question. By controlling the variable in terms of blocking the path, does it mean we set its value constant in our experiments? So, for example, to remove the impact of gender on a drug survey, we make a control group and test group of the same gender. Exactly. Yes, this is exactly the same. Controlling means that we fix the value of confounder, and this is how we control. And then there is no variation in this confounder. So even if it has, like, for a particular subgroup, if we take only females, for example, even if there is relation between the gender and association of the drug, for this subgroup, it is not present because all the elements in this subgroup are of the same gender. Move to the next one. How do we make a causal graph for when we encounter causal cycles in the real world? This I cannot answer right now this question. I didn't research this direction yet, but however, I think it's a philosophically difficult problem in the sense that you have something that controls, this is nicely presented in this picture on the title of the slide. So what comes first, the chicken or the egg? Where should we start from? So my guess is probably maybe such types of questions are not considered, or there is a particular theory. However, I'm not able to give you any hints for now about it. Next question is saying that a grandparent node doesn't give us more information about the probability of the current node. And so we may only take into account the parent node, a Markov assumption. Could you please give any examples of when this assumption doesn't hold? Yeah, this is a Markov assumption. Just let me, I need a couple of minutes to understand the question. So essentially, the way we were decomposing the variabilities, probabilities here, this is all is based on Markov assumptions. And now the question is, can it happen that if we control for grandparent node doesn't give us. If we already control for the parent, is it possible that grandparent give us more information about the current node? Then as far as I see it now, it's if there is a direct link between a grandparent and the child. So I will try to draw it. If I can. Okay. So essentially, as far as I understood the question. So we have some parent, we have some child, and then there is a grandparent. And we say that by controlling on the parent, the information from the grandparent cannot give us any new information about the child. The only way that it can be violated is probably when there is a direct link between the grandparent and the child. Okay, the next question. What is the difference between ignorability and positivity? Actually, doesn't ignorability imply positivity? Okay, let's have a look on the assumptions. The difference is, well, probably you can view positivity as a violation of ignorability, essentially that there is something that defines, so there is a co-founder that defines how the treatment will be assigned. Let's probably see on the example. So we have our treatment. Okay, we have some group, and the treatment is assigned deterministically. It means that there is some other variable that decides if the treatment is assigned or not, like yes or no. So this can be viewed as a confounder. However, confounder is a different thing in the sense that, let me give you an example. For example, I think we discussed that. So if we assign a drug, and the possible confounder can be the age. Like for people above 60, we are more likely to assign the drug than for people below 60. So in this case, positivity holds in the sense that there is a still probability for people above age to not be assigned any treatment. So the assignment of the treatment is non-deterministic. However, ignorability does not hold because there is now additional variable that causes the assignment of the treatment. And it means that from the data, from the things that we observe, the correlation that we observe has information from both causal relationship and also this relationship with the confounder. So these are different things. I hope this answers your question. Okay, the next, could you please explain how conditional probabilities appear? Is it part of definition of causal graph or does it somehow follow from the definition? So this is about the decomposition of the yeah, let's talk probably about the decomposition. Here it is like if we are talking about the decomposition, this is essentially just a rule that how we can do it. But this comes sort of from the common sense. So if we have, for example, this example, then we have we know that C is independent as all the others. So essentially, we try to do something like Bayes rule. When we had, okay, I will open this. Like the Bayes rule, what does it tell? If there are two variables and if they are dependent, the joint probability is the probability of A multiplied probability of B given A. But it also says that it is the same as probability of B. So for observational data, the probability of B multiplied by the probability of A given B. So this you should know from the university standard rule. And just from the probabilities, there is no way for us to distinguish which way should we write. They both are equal. However, the difference with the causal graph is that they represent the direction as well. So we can distinguish which way to go. And following these rules, for example, if we just consider this part, like let's start with probability of C, it is independent, so we just write it probability of C. Then now we have a choice, either to write probability of D multiplied by probability of A given B, or probability of A multiplied by probability of D given A. However, given the structure, we know that this is D that is the cause. So that's why we write the probability of D, and then we add its children. I hope it answers the question. This is essentially the link with the Bayes rule. Okay, slide 20. Slide 20, sorry. Probability of ABCD is equal to probability of D, probability of A given D, probability of B given D. So you're asking if we can write this part probability of C given A and B as probability given A and probability of C given B. Well, in general, if I just see this formula, probably I would say that this is might be not correct, because there can be also a relationship between A and B. But for this case, there is still association from A and B. Well, I'm not sure. I need to check this. I didn't think in this direction, so I will not be able to answer this question. However, it seems to me that because there can be relation between A and B, and for example, A and B here are related via D, I'm not sure if it can be done this way. Next question, what if we want a joint distribution for a subset of nodes? Could you please give some examples? Joint distribution for a subset of nodes. If you take the subset of nodes, like if, for example, we take the case when there is something independent, then we can just remove it. However, if you want to take a subset of nodes, then it means that you have to remove the or not consider the relationship between other nodes. For example, as we saw, even though, for example, here the relation comes from B to C, in the distribution of probabilities, we can see that C and B are related. So if you just remove this connection, then you just have a small graph and you can write it from there. Next question. Is causal graph the same as probabilistic graphical model? Well, I didn't yet encounter the definition probabilistic graphical model, but essentially structural causal equations, this is the same. Yes, if it has the same meaning, then probably yes. But essentially, causal, like we can call the causal graph, as it was said, like any direct acyclic graph can be a causal graph. And so whatever you can infer with the direct acyclic graph will apply to causal graphs as well. Next question. Is the first correlation about the common educatedness? Wait. Sorry, I don't understand this question. Could you please reformulate it if possible? Next question. Do you think assuming consistency is valid, it is not a bit too strong for the applied work? As far as I know, it is proven for each treatment effect estimator. Do you also think that ignorability is really necessary? We can still induce unmeasured or unobserved confounders into the error term. Okay, let's come back to the assumptions. Do you think assumption of consistency is valid? So essentially, all these assumptions, they allow us to define a theory, and a theory that under which it will work. And we have guarantees that it will work. As soon as we start removing assumptions, we are moving towards the guess, and all these assumptions is essentially a debate. Also, for example, in social sciences, then when they present their results, they list the assumptions that they made, they list their clarification, the explanations why they think that these assumptions are valid. And there is a debate afterwards. So there are researches, for example, done, and some people still think that this is not a valid assumption. However, it depends on what you want. So as it was said, and also during the keynote presentation, that we cannot move any further without the assumptions. But we will see, for example, a couple of, so here we had sort of a general framework for how we can identify the causal relationship, but in the end, like in the second part of the presentation, I will talk a little bit more about just how we can identify the direction, whether Y causes X or X causes Y, and there can be some different assumptions. So you will always have to make a trade-off, but like these assumptions guarantee that the theory works. And then in your application, you have to think and decide how much you want to be sure in the theory, or you are ready just to take a risk. Next question, can you tell or suggest some sources where I can read about real world examples, how these more sophisticated examples were applied in real world controlled experiments? So if you are interested, for example, for examples from social sciences, which, because I will be working mostly on this, the next part, we will talk about some particular experimental designs, and I will be giving the links where I took this information from. So you can have, there will be some videos, and in those videos, they refer to some papers, and you can have a look. But I will also give some examples of how this were used for real analysis, and you will also have the references to check later. Okay, the next question. So do we derive properties of causal graph and properties of probabilities not from any definition or axiom, but from common sense? Well, there is a sort of definition or axiom that, like, for example, we use the Bayes rule, but then on which direction to go, that comes from our assumptions and the common sense. At least this is how I understand your question. Maybe it is not what you wanted to ask. Please continue. Just a second, should we continue because it's already time for a break? How do we continue answering the questions? So do we make a break and then probably we'll come back to the questions after the second session? Hello, Alina, do you hear me?
Yeah.
Should we proceed? Like it's time already for the break?
Yeah. 30 minutes.
Okay, then you can continue asking your questions. Then we will discuss them after the second part of the presentation. And maybe, by the way, by the time you will get some answers on some of your questions. Thank you very much for your attention and see you in half an hour. А вже можна починати?
Yeah.
Ще раз?
Yeah. You can start.
Не чую вас. Не можу розібрати.
Можете починати, так.
Дякую. Thanks everyone who joined again. So this will be the second part of the presentation on fundamentals of causal learning. And in this part, I want to discuss experimental designs that were used for causal learning, mostly in social sciences. But I will also then make a link how these ideas might be and are already used in research in machine learning. So I will go through a couple of methods. We'll talk about matching, then incident user design, active comparator, instrument variables analysis, differences in difference, and regression discontinuity, and usage of modeling for causal inferences. So let's start with the first one, matching. So the problem in general, as we saw, is the presence of some confounder variable. So if we have our treatment and we have our effect, everything is great. We already have this relationship present in the data and we can calculate, estimate it, and so on. But the problem comes is from the fact that maybe the relationship that is present in the data shows not only the causal relationship, but something else. Maybe there is some confounder that can impact A and Y, and in this sense, the things that we observe in the data set are not pure causal relationship, but they also interfere with another relationship. Or it may be that this causal relationship doesn't at all even exist, and whatever we see in the data is due to some other common cause that is a confounder. We saw that we can use a theory of causal graphs to identify the set of variables that can be confounders, and there are ways to control, and essentially how we control is that we condition on different values of those variables. Now, assume that we have some data set. It can be either collected through experiment, or maybe, as they say also, the other notion is natural experience, so that have some data set already collected, and it was collected not with the intention to answer a particular question or a particular causal question. So there might be no sufficient control in the way we assign treatment and so on. So the assumptions might not hold, but still we want to try to infer, to use this data set to answer our question. And this is a very promising avenue now, because everybody knows that the amount of the data, available data is growing, and why not to use it, and why to spend time and efforts on experiments if it is possible to infer some from the data. And in many applications, it's either difficult or impossible to run the experiment. So what can be done if we already have the data, and then how we can do the analysis wisely? So again, we want to remove some confounders, something that can interfere with the causal relationship. So we want to do some control. And one of the ideas that can be used for that is matching. And matching is essentially trying to create effect of random assumption in our data set. So random assumption of the treatment is essentially that every person has the same probability of being treated or not. So there is no, like for example, for this small data set, the possible confounders are sex and age, and we don't assign the treatment depending on the sex or age. So that by this way, we eliminate the probability that sex or age can be here as the confounder. They cannot appear here. What is if it is not the case in our real data set? We can try to take a part of this data set to simulate the experimental design. And this is done by matching. So essentially, usually we have, let's assume that we have a small population of treated people who got their treatment. So for them, the value of A is equal to 1. And the other group is also known as control. For them, the value of A is usually 0. Usually the control group is larger than the treated group because it takes some effort to give the treatment. So we have more elements in the control group than in the treated group. And now what we can do, we can try to identify subjects that are similar to those from our treatment from the control group and do the analysis only for them. And like this, we remove the possible aspect of our confounding variable. Like here in the treated data set, we have two subjects, male and female. Male is 56-year-old, female is 47-year-old. And assume that we want to control for the sex and the age. So we can try to identify similar person to this one that was not treated. And then we can compare these two people and evaluate the causal impact of the treatment. So for this case, probably, yeah, so we have our data set with a bunch of males and females, and this one is probably the closest. It has the same sex and very similar age. So we can take these two subjects and assume that because they are the same, like in our hypothetical world now, all the differences that can happen to humans are the sex and the age. So they are essentially the same or almost the same. And the only difference in between them is the absence or the presence of the treatment. So whichever difference we view in the data set, we can associate with the impact of the treatment. And then for the other subject, female 47-year-old, we can probably suggest, so we have female here, here, and here. This will be probably the closest one. So now our data set will, like here we had two subjects, and here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, our original data set had 2 and 10, but we can construct our small data set that will have only 4 subjects. The first male, 56-year-old, and the value of treatment is 1. The second is male, 55-year-old. The value of treatment is 0. The third is female, 47-year-old. The value of treatment is 1. And female, 31-year-old. The value of treatment is 0. And then we will analyze only this data set and the relations that we extract from this data set, we can attribute to causal relationship because other confounding variables were ruled out. The possibility to find a good match depends on your data set. So for example, here in the second case, the two subjects are not very close. The difference in age is different, but is quite big. But it all depends on the application and your assumptions does it really make a difference in this case or not? There are also different designs, like we can do one-to-one matching or pair matching. This is essentially when one person is matched from the treated group is matched to exactly one person from the control group. One-to-many from the name implies that we match one person to many a bunch of other people. We will discuss a bit more these differences on later on. So now there are a couple of ways you can do that, very simple algorithms, just to give you an idea that this already exists and this approach is already implemented and you can even use them. There are libraries in R for sure, I think in Python as well. A very easy solution is the greedy matching. So what are we doing? We're just ordering the list of subjects, usually it is from the treated group. Then we order the list of subjects from the control group, and we process the subjects one by one. We take the first one, we select the best match for the first one, and we remove these two lines from our data set. And then we repeat this process until we have a match for every subject from the treatment group. Let us consider an example. Assume that we have such a data set, so we have variables age. This is the particular value if they had a particular medication or not, and the sex. And this is our treated group. So for this group, A is equal to 1, they got the treatment. This is our control group. For them, A is equal to 0. So here we have two subjects, female and a male, 78 years old and 60, almost 8 years old. Here we have 6 people, 3 of them are male, 3 of them are female. Now we start processing. So assume that the data sets are already ordered. So we start processing from the first one. And now our task is to find somebody who is the closest from the control group to our first subject, this one. For this, we can calculate some distance functions. It will also depend on your application domain, but essentially it can be Euclidean distance. The only thing that you should take into account is the fact that some variables can have a very large range, while the others not. Like, for example, age can change from 0 to, let's say, 100, while sex has only 2 possible variables. And probably the difference in 1 unit between the sex is more important than the difference in 1 unit between the ages. So you need to construct distance functions depending on your application. So let's assume that we somehow calculated the distance function. Let's say this here, distance 1. And so the distance with the first subject from the treated group, and let's say it is, the values are 4.2, 0.17, 372, 245, 289, and 3.6. As we said, we want somebody who is the closest, or somebody who has the minimum value of the distance, and just analyzing these values, we can see that this will be the second subject. So we will choose this person, and we can start constructing our final data set that will be used for the analysis. So it will be the first subject from the treated group, 78 years old. The value of the second variable is 0, then sex is female, and we take this person, 75, 0, 1. And the value of treatment, first one is treated, the other one is not treated. Then we remove these 2 lines from our consideration, they're not there anymore, and we do the same thing with the second subject. So we calculate the distance 2. Here we can do the calculation. Let's assume the values are 3.7, 2.0, 4.3, 0.78, 1.45, and 3.6. By the way, for this value, we don't even need to calculate it because this element is already excluded. And we find that the next smallest value is this one. So we can finalize the construction of our data set. It will be 67.9H, 0, 0, treated, and the other one 54, 0, 0, and untreated. And then we will do our analysis on this data set. So this approach is a very simple, intuitive, easy to implement, not very computationally expensive. However, it is not optimal in the sense that our solution will depend on the ordering, on the original ordering of our list. For example, if imagine that the value of distance here would have been 0.1, then if we start with the first person here, this element will be already rolled out. So we will not even consider this subject as the possible match for the second one. While if we start with the second person, it will get the first match will be this person, and then the first person will get a different match. And it is not optimal in the sense that if we tend to minimize the total distance, that is the sum of all distances, like here, for example, it is for the first pair 0.17. For the second pair, the distance is 0.78. So the total distance is the sum of these two values. And if we aim to minimize the total distance, then such approach will not give us an optimal solution. So there is another approach that is optimal matching. And it's essentially, we do the global optimization. It should be clear how it works. Let's just consider a small example. So we have a set of treated, and let's assume that we have only one possible confounder, that is H. The possible values 45, 38, 45, 38, 41. Our group of controls has 12 subjects with the age 72, 44, 60, 63, 35, and so on. So now, if we do the greedy search, we start with the first one, 45, and then the closest subject from the control group will be this person of the age of 44. So we have 45 here and 44 here. Then we proceed to the next one, 38. The closest will be 36. So 38 and 36. And finally, 41. The closest in this case will be 47. So 41 is associated with 47. And then if we calculate the total distance, so here it is 1, 2, and 6, so it is 9. But if we do the optimal search, that is, we analyze all possible combinations for which element to start, then we will find a different solution. We will associate 45 with 47, and 41 with 44. So essentially, these two will be replaced. And this subject will get the same match, 38 versus 36. And now if we calculate the difference, it will be 2, 2, and 3. that is 7. So the global difference here is less. For those of you who come from the computer science background, you should know the difference essentially in between these computational problems. Optimal search versus local search. Of course, it is more computationally expensive, but again, it depends on the application that you are working on and your objectives. There are also existing implementations for this approach, and sometimes this can be made. This computation can be made easier if we do additional assumptions. For example, we can match within certain blocks. What it means. For example, here assume that there would have been additional parameter that is the country where the person lives, and we want to match only within a certain country. So people who live in Ukraine should be matched with those who live in Ukraine. This will reduce the search space of all possible combinations and will make it the process faster. Also, we can allow some mismatches in the case that we still have a good balance of distribution of variables. And this, again, is already implemented. It can be already used. There are packages that implement these things. Now let's discuss a little bit about one-to-one matching versus one-to-many matching. So essentially, one-to-one, we associate one person with another person, with one more person. Many-to-many, we have one person, usually from the treatment, there is one, and many people from the control group. What are the drawbacks and positive sides? Of course, this will be faster because we need less computational operations, and probably those matches that are found will be better because we always take the best match. So essentially, the best match corresponds to the first match, and the others are already, at least they are not better than the first one and probably worse. However, many-to-one takes into account more larger data set and probably more information that is there. So essentially, it comes down to the trade-off between bias and variance. In one-to-one, we are less biased because the subjects are corresponding to each other very nicely, while in many-to-one, we have much more variance and we can do more conclusions, but it is questionable if they are reliable. The next experimental design is called incident user design. These are the approaches that are used, and as I said, there will be links where you can have a look on the explanation, for example, this one. And so we will consider some examples. Assume that we want to evaluate how yoga affects the health of the person. And we can collect the data set about the people who have practiced yoga during some period of time, and then also evaluate how healthy they are. But then there are a lot of questions that come into a picture. For example, this person started practicing yoga, but then it stopped, and maybe because it didn't work for him, so there will already be some confounding. Or this person, he practiced for quite a long time, and even though he is not practicing now, maybe he still has the possible positive benefits of practicing yoga on his health. So a lot of questions come into picture, and one of the possible ways to control for it is to take only new users, so the users who just initiated the treatment. So in this case, we will consider only those users who just started practicing yoga at a particular point of time, and then we can compare with those who didn't do it. Like this, we remove possible confounders of if the person practiced here, it is still possible, has possible outcomes or positive outcomes, or for example, no, he already discovered that this does not work for him. However, there can be problems with the comparing with the other group, in the sense that maybe people who are practicing yoga are in general more people who are interested in sports, so more healthy, and their health is already in a better shape. So we can add one more condition, and it is known as active comparator design, and it's essentially comparing with another type of treatment. For example, we compare people who are practicing yoga with those who are practicing Zumba class. In this case, we change the causal question. So now we don't compare the fact of practicing yoga with not practicing anything, but we compare effect of practicing yoga with the effect of practicing some other type of sport, but we can be more precise about the results. There will be less confounding, and our solutions probably will be stronger. And many times these two designs can be used together. So this is the first approach. Now, another approach very common in econometrics is instrumental variable analysis. Has quite a lot of assumptions, but we will try to go through them and understand why it makes sense. And again, you can check an example following this link. And so this will be a YouTube playlist, and there will be additional examples of how this approach was used, and some quite interesting examples that may be useful for you. So what are the assumptions that we want to make? We assume that there is some variable that we call instrument, and that it correlates with the outcome variable. So we have some instrument, and there's some visible relationship with the outcome that we see in the data set. That instrument has causal effect on the outcome. However, it has no causal effect on the treatment. Instrument is randomly assigned, or we can assume that it is randomly assigned. And from this random assignment, we can also assume that causal impact of the instrument on the treatment is reflected in the correlation. So essentially, because it was randomly assigned, there is the correlation that is available the correlation that is there shows the causal relationship, and that instrument is not correlated with any other possible confounder except for the treatment. So let's have a look on the possible graph and how these assumptions come into place. Assume that we have some instrument variable, then there is some treatment. This is the variable that in the effect of which we are interested, and some outcome, y. So we want to measure the causal impact of treatment on the outcome. However, there might be some confounders, pre-treatment variables, that might have causal relationship with treatment and the outcome. And in this case, it opens the backdoor path. And as we discussed before, it will make it difficult for us to evaluate the causal relationship between treatment and the outcome, because there can be other relationships interfering, and can magnify them or even inverse them. So in general, there can be also causal links between all other elements of our graph. So we'll draw them, and then we'll start the analysis. So as we said, instrument does not have causal effect on the outcome. It means that this error doesn't exist. There is no causal effect here. So we can remove it. What's the next? Instrument does have a causal effect on the treatment. So this error is there. Instrument is randomly assigned. So it means that the assignment of the instrument doesn't depend on the treatment effect. So this relationship is gone. now this is what we have, and we know that there is some relationship visible in the data set between the instrument and the outcome. But we know that this is not a causal relationship because we said it as stated here. We assume that this is not a causal relationship. So whichever correlation we see between the instrument and the outcome is due to causal relationship between the treatment and the outcome, plus the relationship between the instrument and the treatment. But this we can identify from the data set. This we can also identify from the data set, and then just subtracting sort of this part, this impact from this one, we can identify, we can estimate the causal effect of the treatment on the outcome. And in this case, we can forget like this, the presence of pre-treatment variables and the possible confounding is not a problem for us. And this is very useful in the cases where it is just impossible to identify all possible pre-treatment variables, so there is no way to control for them. Let's have a look on how it works in the example. So assume that we want to evaluate what is the impact of education on the amount of money that you earn. And assume that from the data set, we have some clearly correlated pattern. It seems like a linear relation with a nice correlation. However, are we sure that there are no possible confounders? Maybe it's the ability of the person, like inner ability, that both makes the person study more and allows him or her to earn more later in the life. Maybe education doesn't cause higher earnings, it's only the ability. And usually such things are difficult to measure. So these are possible confounders that are difficult to measure. In this example, we assume that we can do it, but in reality, we don't have to do it. We just need to justify that we follow the assumptions of the instrument variable analysis. So here in this case, what we see, let's move to another graph. We will analyze, so this is our possible confounder, ability, and we want to see how it is related to education and the amount of money that we earn. Once again, this is a simulated data set, so we can evaluate it here, but in general, it might not be possible. And again, we see that there is a correlation. So it might happen that indeed it's not the it's not the education that causes the difference in the amount of money you earn, but the ability that does that. So we can, this is an example of analysis that was made a couple of times in social sciences. And again, by following this link, you can check the presentation of this approach, and in particular this analysis. And I think they also cite the paper, so you can find the papers where this is done. So we want to use the instrumental variable analysis, and here we will need to argue that the assumptions hold. Let's assume that we take as the instrument the distance to college, distance to the college or the university. Now we need to argue that this instrument indeed corresponds to the assumptions that we have posed. First of all, we need to have correlation with the outcome. This can be identified from the data. You just take the data set and you plot two variables, distance to college and education. And in this case, we see that, yes, there is indeed a correlation. So we can work with something. Then the next assumption, instrument has no causal effect on the outcome. So in this part, we just need to think. Let's just think, indeed, will distance to college affect the amount of money that you earn later in life? And probably it's possible a good argument that not, because your boss, when defining your salary, is not at all interested in how close you lived to a higher educational institution. It's only the performance that will affect your salary in the best case, but at least distance to college definitely will not do that. So this assumption is also holds. The next is instrument has causal effect on the treatment. Sorry. So about the first assumption, this is in fact represented on the second graph here. Instrument correlates with the outcome, because our outcome, we want to estimate how much more money we earn. So the outcome for Y for us is Y, wage. And the instrument, our instrument is the education that we want to test. So for the first assumption, there is correlation between instrument and the outcome. Our instrument is the distance to college, and this is our outcome. And indeed, there is a correlation. Sort of people who live closer to college tend to earn more money. Then instrument has no causal effect on the outcome. This is that we discussed, that essentially, well, when your boss is deciding whether to give you larger salary or not, he's not at all concerned about how close you live to the college. Then the next assumption, instrument has causal effect on the treatment. So first of all, we can check if there is a correlation from the data set, and indeed, there is a correlation, but also we can think in the sense that why should distance to college have any causal impact on the education? And it might be explained by the fact that people who live closer to college have higher chances to attend, because, for example, they have to spend less money. They don't have to move to a different city to study or a different place. They can live in their home, or they are more exposed to other people with higher education, so they might be more interested. And the last assumption, that instrument is randomly assigned. So essentially, it doesn't depend on the covariance. And in this case, it was the ability that we assumed might be a covariance, something that causes both higher education and higher wage. And because the data set is simulated, we can check that from the data set, indeed, there is no clear pattern, but also in reality, we will not have access to this information, but this can be done as a thought experiment. Like, why should distance to college depend on the ability? If people are randomly born in different parts of the country or of the city, the child who is going to have higher ability will not impact his parents to move somewhere closer to the college. And here I will give you an example of how these assumptions can be debatable, because another point of view, how you can look at it, is that those people who live closer to college, they might be working in the college, and they might already be professors, and so they might have children to whom they will pass the genes of this of the ability. So you will have to always have a trade-off between the absolutely correct truth that I know that this is a causal relationship and there is no other way, and the assumptions that you make. Like in this case, for example, there is a debate between professionals if indeed there will be no relationship between ability and distance to college, but assume that it is not there. In this case, all the assumptions are satisfied, and we can then estimate. We see that there is a distance to college that impacts the wage. However, we know that there is no causal relationship. But then we see the link between the distance to college and education. So this relationship we can attribute only to the causal relationship between the wage and education, so that education has a causal impact on wage. So we can estimate the parameters of this relationship, then of this relationship, take appropriate corrections, and then estimate how education will impact the amount of money that you earn. So this is a very commonly used method, and here the problem is to come up with a very good instrument to be able to argue that, that these assumptions will hold true. And sometimes it requires a good understanding of the domain knowledge, but if it works, the good thing that you achieve is that you are not at all bothered about confounders. And even like one of the assumptions that we made, that there are no unobserved confounders. Even if there are unobserved confounders, in this case, you can sort of overcome them because you will be evaluating your causal relationship through a different path. So even unobserved confounders is not a problem for this approach. This is all for the instrumental variables, and now we'll have a look on differences in difference. This is an approach that is used when we have some information that is changing through time. Let's have a look on the example. So again, this is example taken from this video. You can check, and there is a reference, at least the paper, original paper is mentioned, and a couple of other examples are mentioned, so you can check them in details. Here they analyze the impact of death penalty on the rate of crime. So in before this date, 1975, the death penalty was banned. This is about US, was banned in all US states. And in this year, some of the states allowed death penalty. So now we want to evaluate how did it impact, how did the fact that the death penalty was allowed impact the rate of the crime. So some people think that if there is a death penalty, the criminals might be more afraid of this penalty, and so they will be less likely to commit a crime. Here we have the corresponding rates for two groups of states. These are the treated states. It means that these here is the value for those states that didn't have the death penalty in 1975, but then introduced it in 1977. And these are the states that didn't have it in both cases, and these are the main values through all those states. So if we just compare, we want to compare what is the difference. If we have the treatment, we can just take this treated states and evaluate what is the difference. And for that, so we take what will be the impact. We take the pre-treatment 10.3 minus 9.7, and this will be our impact. So it is 0.6. Yeah, 0.6. So from this, we can conclude that the introduction of the death penalty, in fact, allowed us to decrease the crime. We took these values and we got this result. However, let us see what happened, for example, in the untreated states. So for these states, nothing changed. They didn't have the death penalty before and they don't have it now. So what is the difference in this case? So we take 0.8 minus 6.9 and we get the result 1.1. So just a change in time reduced the amount of crime. The other thing that we can do is to compare untreated group with the treated group at the time when the death penalty was introduced. So we take 6.9 minus 9.7, and in this case we get minus 2.8 if I'm not mistaken. Yes. So here we can see that if we compare in 1977 the untreated states that are those that didn't have a death penalty with those who introduced death penalty, then we can see that the relation is in fact contradicting to the previous one. That is, from this part we can make a conclusion that introducing the death penalty in fact increased the rate of the crime. So what is correct? In this case, we can use the common trend assumption and assume that there is something something happened during the time that also impacted the change in the crime rate, and this something is the same for both treated and untreated groups. However, the additional difference can be explained by the treatment. So in this case, if we just we can estimate the trend, the common trend. So what should happen normally without changing the system? It is 1.1 when we compare to these two cases. And now, so this is the common trend, the thing what was supposed to happen. The decrease is supposed to be by 1.1, just the common trend. However, here it is also reduced by 0.6. So additionally, we now subtract, sorry, so we do it differently. So we have here our change is 0.6. And then we subtract, this is the combined change of the trend. Something was happening just due to the change in time and the effect of the treatment. From it, we subtract the part that is the common trend, that is the common, and then we get the result. And the result will be minus 0.5. So in this case, in fact, introduction of the death penalty increased the crime rate, but not as much as it could have been estimated from here. So here, let's now talk a little bit about the common trends assumption. It is essentially when we assume that for certain we have treatment and control groups, and there are some changes that are happening in time, but they have the same impact on both the treatment and the control. However, at some point, so they move somehow, for example, like this. However, at some point of time, we introduced the treatment. So we changed something in our system. For example, let's say here, we did some change, and now the values changed. The trend changed. So because the only thing that is now different in between these two groups, treatment and control, is the application of the treatment, we can associate the difference that occurred. So this will be this difference, or here it will be this difference, with the introduction of the treatment. This is the common trends assumption, and I think such things can be also used in when we write our analysis of machine learning applications. In some cases, we can also use these ideas. Next approach is regression discontinuity. This is again another way to control for possible confounding. Let's again, you can check this example following this link. Let's once again analyze an example. This is an example that is very common and is also given on the Wikipedia page if you search for this experimental design. When we try to evaluate, for example, the impact on your social status of some social recognition of your achievements. For example, the experiment was done with the high school students. At the end, they were supposed to pass, they could have passed the test, and if they get a particular mark, they get a certificate of merit. And if they're below some threshold, they don't. So essentially, that doesn't give them anything apart from the fact that somebody recognizes their abilities. And then they have a particular diploma that can be used when they're applying for college. They can use this as the proof, or their names are published in newspapers and so on. And if now we want to evaluate the impact of this social distinction on what happens later in life, it is very difficult to separate the impact of your abilities on what happens in your life. For example, here, to get a proper to get a merit certificate, you are supposed to have a good knowledge and be able to pass that exam. So, for example, here at this point, people don't have good knowledge, so they have lower values. However, here they have better knowledge, they're better prepared, they have higher values. But we can concentrate on this middle point. Assume that the threshold is, for example, or we can have the values from 0 to 20, and the threshold when the person gets the certificate merit or not is 10. It is clear that there is a big difference between a person who got 1 and the person who got 19, for example. There is a very big difference in their abilities and their knowledge, and of course it will impact later their the fact if they go continue the education or not, and how much money they earn. However, the difference between people that are just on the edge is not that big. This can be just the person didn't sleep well before the exam, or he was nervous because there is maybe just some decimal fraction of the grade that he lacked to get the certificate of merit. So here we will be comparing people just after the edge and just before the edge. And we assume that there are no possible confounders because they are very, very similar to each other. And like this, we eliminate the confounders like ability or something else that can also impact. Another example of such analysis was done to answer such question. Will the quality of school affect the prices of the house? So this is again an example from US. Assume that we have some city and we have some districts, and every district is associated with a particular school. And if you live in this district, your children are supposed to go to this school. They have different schools. And then now schools are different, and this can be estimated by taking the average test results of the students and so on. So there can be a lot of differences, but for example, we can compare the houses that are just on the edge. There will be the same in many other confounders, like for example, if there is a park nearby, the both houses will be close in the same way close to the park. And the only, taking into account some additional assumptions, the only difference that we will observe here is just due to the fact that if you are living 200 meters up, then you are associated, for example, with the better school. So this is another way how this approach is used for the analysis. Also, it has hard and soft designs in the sense that we can take only the elements close to the edge, or take some more elements below, but no, not below, but a bit farther from the edge. But then we have to control somehow at additional weight. In general, I think it's a very interesting approach, and also can be used in our applications when we do some analysis, data science analysis. This idea can be used and very useful, and it already exists. We can use it. And the other thing is that there is also a theory behind it, that how we should compare these two things, just close to the border, what things we should take into account, how to compare the difference, and so on. So we can already benefit from this theory that is developed and use it in our research answering our questions. Another, this is the final approach, that is called modeling. So we talked that the best way to identify causality is via randomized experiments. It is not always possible, for example, to conduct the experiment, but at least we can collect the data that is as if it was experiment. For example, we have some people who were treated and who were not treated, even though it is not exactly the same person. However, we can assume that potential outcomes are equal to the observed outcomes. But in some cases, it is not possible even to collect the data from the natural experiment, because this experiment will never happen in the nature. And a very good example is when we are studying the impact of humans on the global warming. There is no way for us to have two planets Earth, and one planet assigned to have people with it and another not. So there is just no way neither to run this experiment, nor to for this experiment to happen in somehow on its own, and that we can collect the data about it afterwards. The only way that how in this case the causal learning can be done is through modeling. Essentially, in this case, we are supposed to create the model and take into account all possible factors that can impact and model how humans will impact the change in climate, and all possible other possible variables like solar activity, maybe activity of other living beings on the planet, and so on. And in this case, the quality of the model is very crucial, because essentially the fact that we can make any assumptions will depend on how valid the model is. However, it is the only possible way. Another thing, it can be very complicated to construct this model, because we need to know, essentially we need to know what are the mechanisms, and we have to justify that they are like this. But when, for example, we do the randomized experiment, and we just want to evaluate the impact of the drug on the some recovery rate, we are not even interested, in fact, how exactly this drug affects the human, how exactly it fights with the disease. For us, we just want to evaluate the impact, and this can be done from the data. We don't need to know any additional information about the mechanism, the physical mechanism that is behind. From the other point of view, modeling allows to do extrapolation, that is doing some analysis beyond just the things that we observe. That is, for example, from the same example, when we are evaluating the impact of the drug on the health, this will not tell us anything of the, like if we do some experiment and then we want to change something, for example, we evaluated the impact of the drug on males, it tells us absolutely nothing of how it will impact on the females. But if we do the modeling, we understand the process before, and this knowledge will be already inbuilt in the system, and then by constructing a proper model, we can do much more inference than without it. This is the last approach that is used for causal inference in social sciences. At least this is what I wanted to present. And now the last part of this talk, I would want to talk about relationship between causal learning and machine learning. What are the current trends? Some things that I want to share with you. So one of the questions is it possible to define the direction of the cause? And sometimes, in some cases, it is true. And in fact, we need very minimal assumptions. We will have a look on a couple of examples now. Assume that we have two variables, x and y, and we have some data set, this data points in blue. And we know that the relationship between x and y is linear. And we know that there is some noise, an additive noise. However, we don't know the direction of the relation. Is it x that causes y, or is it y that causes x? So if we assume that the noise is additive and it is independent, then we can, in fact, derive some conclusions. So this is these lines are not just drawn. This is a real like simulated data set, but these two lines, orange and red, are not just drawn. They're estimated by least linear squares regression model. And the red one is the regression model for the first case when x is the cause and y is the effect. We get this red line. After that, if I assume that y is the cause and x is the effect, I obtain a different regression line that is represented in orange. Now, what we can do, we can plot the residuals as a function of the causal or independent variable. So for the first case, the first model, this will be the difference, for example, in between this point and this point on the line, because this is how we estimate the regression. And we can calculate it for every data point in our data set, like this, like this, like this, here, here, and then plot it. And this is the plot that we get, the dependence of residuals on the x. And we can see that there is no particular structure. It seems like to be independent. However, now let's analyze the other model. We think that y is the cause and x is the effect. Then the way our regression line is orange. I will just change the color. So this is our regression line is orange. And the way we will be calculating the residuals, because we are now regressing on y, will be done in this way. These are our residuals. Here, here, for example. You can check it later after lecture with your example. And then we can plot these residuals. They are shown on the second graph. Here they are. And here we see that there is some structure, there is some dependence. So the residuals is dependent on the causal variable in this case. But we assumed that noise should be independent. So in this case, we have two assumptions: linear model and independence of noise. And these two assumptions are enough to conclude that this model is not possible, and this one is the valid model, and it means that it is x that is causing y and not vice versa. Let's have a look on another example. Again, we have two variables, x and y. We don't know what is causing what. Now we'll try slightly more complicated model. It will be a quadratic model. Either y is a square of x plus some additive noise, or x is the square root of y. If we just invert the functional dependence and we solve the equation, this is what we get. And again, assume that the noise is additive and it is independent on the causal or independent variable. And again, we can construct the two lines, two regression lines. These lines, again, these are real regression lines from the data set that are shown on the slide, not just random lines. Again, we can calculate the residuals. For the first case, they will be calculated like this from the red line to the real data points, like this, for example, like this, and we can construct them. This is what we get. So we see that the variance changes, but the residual itself doesn't change depending on X. However, if we analyze another regression model, that is, this will be orange regression line, and the way we calculate the residuals are like this, this direction, and then we do we plot the relationship. This is what we get. So now we have some relationship. There is some functional dependency of Y or of residual on Y on the causal variable. Again, this violates our assumption that the noise is independent. So we can exclude this option from the consideration, and this is the model. This is the correct causal model. Now, a couple of other types of assumptions that can be used to identify the direction of the causal relationship. One of them is simplicity assumption. Essentially, from its name, it's very simple. And what it means is essentially that the model is simple. There is no need to complicate the model. So let's once again have a look. We have the distribution and we have two variables, X and Y. And we want to know what is the cause and what is the effect. And if we assume that Y is the cause and X is the effect, let's, for example, have a look here. We see that for a particular value of Y, there are different clusters of possible values of X here and here. So the model has a sort of different possible values. It is not functional model, but it's also more complicated model. At the same time, if we assume that the X is the cause and Y is the effect, at every point of time, we see that there is only one cluster of possible values of Y for a given value of X. Again, we can argue whether these assumptions are valid or not, but this is something that can be used in practice. Now let's talk a little bit about assumptions. So in fact, for the whole course, we were talking about different types of assumptions that should be made. Otherwise, we cannot make any conclusions and distinguish between correlation and causation. And it might seem that in the machine learning as we know it so far, the assumptions, there are no such big assumptions. However, it is not true. And for example, our traditional regression model, very simple machine learning techniques, does depend on the smoothness assumption, for example. So we assume that there is some smooth function. Otherwise, it is possible to construct whichever complicated function to represent this data set. So the things that we are already used to, with which we are working, which are normal for us, also rely on assumptions. Or for example, if we do the gradient descent, is essentially we calculate the gradient direction of the gradient, and we assume that it doesn't change too fast or something like this. Otherwise, we will step over. We assume that a trend that was in the past will also continue to be in the future, and these are also quite fundamental assumptions that we are using. Now, what about these techniques that I showed today, these experimental designs? In fact, some of them are used I found some papers, and even I also have one paper related to that. This is it. Which try to incorporate these ways of designing experiment to give some causal meaning to traditional machine learning techniques, like where there are works on causal decision trees, causal rules, causal association rules. And also they are used in some real application. For example, you can check a presentation of Amit Sharma here, where he explains how he uses some ideas from the causal experimental design to evaluate real applications while doing a postdoc at Microsoft Research. So these are the things that we definitely can use, and I think what is also more important for us is to know that these things already exist. We should not reinvent the wheel. Also, in the field of social science and statistics, where the causal learning is already an established part of the research, they also try to answer some theoretical questions about which kind of conclusions we can make, what additional assumptions should be done, how we should calculate the treatment and the effect. And we definitely, while working on causal machine learning, we should build upon the results that are already obtained. Yes, it will make it faster and the process and more productive. And this will be the final slide. So a little bit about, I am also discovering this relation or this research direction, causal learning, but what I saw so far, what can be interested, so what people are working on is trying to, there are a couple of directions that I can identify, that people are trying to identify the structural causal model, that is the causal graph from the data, and see under which conditions it can be done, or for example, for a particular type of distribution, it might be not possible to identify uniquely a particular causal graph, but we can say that it depends or it belongs to a certain group of graphs. And the true group is definitely among those that are in this group. Then trying to identify again from the data the causal functional dependencies. There are also attempts to design algorithms for thematic identification of structural causal models. It is questionable how they work, but they also build on those assumptions that we discussed with you, and there are already some packages available. It can be a very interesting idea to see, because this is what essentially we are trying to do in machine learning, to automate the analysis. And is it possible to automate also causal machine learning, in the sense incorporate those assumptions and so on? And there are even some competitions on the techniques for thematic identification of causal relationships. And as I mentioned, people are trying to work on blending together machine learning and causal learning, essentially make machine learning techniques that will learn not just correlation, but causal relationships as well. Why causal learning can be useful, and why should we think about creating causal machine learning? First of all, of course, it will improve the quality of the predictions, because it should not be a surprise that when we use a real cause as our characteristics, the quality of predictions will improve. The other thing is about better understanding of the model, and these directions can help us with such issues as interpretation of machine learning models and such questions as fairness, because we will be able to control for a lot of things. Why I also find this research direction very interesting, because as probably many of you, at the beginning in my head, I had an idea that correlation does not imply causation, but now I discovered that in some cases it does. And it is very interesting to see the limitations and possible boundaries, how much we can push the boundaries and how much we can identify from the data. And trying to answer this question, I find very interesting. Then it will allow us also to develop new techniques that probably will be more robust. As I said, it's very interesting to find limitations. So what are all possible assumptions that can be made, and under which assumptions it is possible to say that correlation does imply causation? And by the end, I think that even though this field is just developing, it is very new, but I think for any practitioner in data science, they at least should be familiar with these things, that they exist, to know at least under which conditions the correlation that they identify can imply causation. That is all that I prepared for today. So I finished a bit earlier, but we will have more time for the questions. Thank you very much for your attention. I will open the questions now. Okay, so causal model, Bayesian network, graphical model, what are the differences? So as I mentioned, I'm also discovering this research field, and now today I shared with you the things that I already learned, that I found interesting and useful, but I need more time to be able to answer these questions. Definitely, as I mentioned in one of the answers, Bayesian networks, very important. It's sort of like a baseline, and my guess that it might be the same, but the causal model and graphical model, this is essentially the same thing. So as I said, we are working, like what we need is a directed acyclic graph, and then you can call it causal if you try to represent causal relationship with it. And then graphical models are just the models that are used to analyze the causal relationship, but it essentially will be the same thing. Next question, in greedy matching, why do we need to cancel the matching elements from our list in the next iteration? It will depend probably on your experimental design, but essentially if you don't cancel, then what are you going to compare? You are going to compare the a couple of treatment subjects with the same, for example, control subject. So let me open it, maybe it will be easier to discuss. The same, by the way, is also done in optimal matching. And the idea is here essentially is to construct a sub data set that will have will have less confounding, in the sense that the elements will be the same on those variables that we want to control. For example, here's age, this medication, and female. And if you don't exclude, then you will have two entries with the same person. So it is then questionable, like, what are you measuring? Does it make sense? So I think it might make sense in some of the applications, but it depends. You need to think of what you are trying to measure, and can one subject be analyzed as multiple or not? Next question. Do you know any applications of causal machine learning rather than classical approach in classical clinical trials in production? Can you please suggest any source for education on this topic? So personally, I don't know in the sense that I read there are papers, of course, and clinical trials, if you are talking about the medicine, this is what they are doing. Like they're trying, this is essentially what they're trying to evaluate when they construct their experiments. However, my guess is that when the question is about health and the medicine, they will more opt for experiments because their price is too high to pay. So we'll probably more opt for experiments than for inferring the data from natural experiments or the data that is already collected. That is more common probably for social sciences in like economics and sociology. However, just to maybe to do initial analysis and have some justification, I'm sure it is done because there is literature I saw, just I didn't pay much attention to that. Probably you can Google and check what is available there. But a lot of things, for example, if you're interested in other modeling approach, you can check such field as econometrics, a part of econometrics. They're explaining a lot of this experimental design. Next question. My question is also about ignorability, positivity assumption. Could you maybe provide more examples? For instance, RCT, where treatment is assessed to microfinance for some communities. Isn't the belonging to these communities a deterministic characteristic? Thank you. Okay, I will try once again. So again, positivity and ignorability assumption. If I'm not mistaken, from this example that you are providing, microfinance for some communities, isn't it belonging to the communities a deterministic characteristic? Belonging to the communities, yes, but then what are you measuring? Because it's the assignment. Just let me think a second. For example, in this case, when we assign the microfinance to some communities, what are we going to measure? Then it is not possible for us to measure the impact of communities on how the treatment of what will be the outcome essentially. Treatment is assignment, not deterministic. So essentially, in this case, belonging to the community becomes a treatment, yes? Like, because positivity says what? The treatment assignment is non-deterministic. So belonging to the community is deterministic, but then we are talking about treatment. So essentially, it means that we want belonging to the community to be a treatment, but it will not be a treatment in this case. So you are probably confusing the treatment with some confounders and so on, or with the groupings. Essentially, positivity, what it means that our treatment, like, maybe try another example. Our treatment is assigned in the same, let's say like this. We have all people. Treatment assignment is non-deterministic. Essentially, if we assume deterministic assumption, all females get the treatment. So A is 1. All males don't get the treatment. A is 0. Then we cannot measure the impact of being a male or a female on the outcome. we say that the treatment, so in this case, we thought that, female male probably not a good idea here. Yeah, but okay, we can even do it with this example. So there is no way for us to understand how being a fellow female impacts the fact that we the effect of the treatment. That's all. So essentially, this means that if we want to measure the effect of the treatment, there should be variation. So we should assign it to, if you're saying about the finance, there is a group who needs money and the group who doesn't need money. But we want to measure how giving money will impact their development. And if you give money only to the group who needs money, you will measure somehow something, but you don't know, maybe there was other things that impacted it. Like, for example, we need to also have some people who need money and we don't assign the treatment for them. And like this, we can compare and see what is the impact, what is the causal impact. So there should be some randomness in the sense we should have assignment of treatment vary for the characteristics. Otherwise, there is no way for us to see how what is the impact. Okay, I hope this answers a bit the question. Maybe another one. So, are there good benchmarks for evaluating a causal machine learning model? There are. Maybe I don't know good or not good, how good they are, but there are. I will try to prepare some links and then share with you. There are some. There were also competitions, COSME, and there are sometimes competitions. Recently, there was a competition on something about climate change. The keynote speaker participated in it. So I will have to check what are the available resources, and then I show you how share with you how good they are, how good they are being benchmarked. It is still questionable because this field is only developing, but according to the current knowledge, it exists, but you still have to invest and understand if it really will allow you benchmarking or not. Next question, is it possible to come up with a causal graph that always has a backdoor path from the treatment to the outcome independently of the set of variables we control for? And what would be the implications of this in a real experiment? I don't think it is possible to construct a causal graph that will always have a backdoor path, because you can control for everything, and then there will be no backdoor path. That's all. Because you can control for all possible variables, like for example, if we take humans, you can control for age, for sex, for the place of birth, for color of the eyes, for DNA, and then there will be just no way for backdoor path, because there will be nothing else that differs. Essentially, it will come to this hypothetical situation when you do assign the treatment and don't assign the treatment to exactly the same person under exactly the same conditions, and then there are no backdoor paths. Next question, what is the conclusion on instrument variable analysis? The education causes wage or not? What picture would we see in the opposite case? For the instrument variable analysis, in this case, yes, the education causes wage, it is correct. I will come back to those. The idea of this was just to show you how it works. This is simulated data, so not a real data. So don't take these conditions as or conclusions as real ones. However, this is a simulation of some studies that have been done, so it is more or less makes sense. What picture would we see in the opposite case? If it, look, so here you will not see the picture, but it's essentially in the opposite case, if there is no, maybe one picture you can see. We, like here, what we assume. we assume that there is correlation with the outcome. If you have the correlation with the outcome, this is the first assumption. If you have the correlation with the outcome, and then if all other assumptions hold, essentially we say that it is not a causal relationship, and it cannot be explained, and the instrumental variable is random, that it is not a confounder, then there is a relationship. Because all these assumptions say that there is a relationship essentially between the instrumental variable and the outcome. And other assumptions allow us to say that this relationship cannot be explained otherwise than the causal relationship with treatment with the outcome. But if there were no, for example, correlation between instrument and the outcome, so we would have some image like here, then there would have been no relationship, and you would have something like this picture. Or if some of the conditions, assumptions don't hold, then again, you can say that in this case, you just cannot conclude. That's all. You cannot conclude that there is a relationship. You cannot make any causal inference. Next question. Is reducing the set of ages related to reducing vector dimensionality? Slide 34. Thank you for your feedback. In fact, no. The question is not about reducing dimensionality. It is about removing confounders. It is about removing other things that can impact the relation between treatment and the effect. Let me see how I can explain you. So essentially, for the data, if you created this data set, and then you will run, even you can run regression to estimate the causal relationship. So it is not about, there is no difference for regression analysis how many data points there are. These are just data points. But it is about removing, if we have some, for example, what is here? Let's assume, okay, let's assume that this is essentially comes to such scenario. I take one person, one 30-year-old person, and I take 60-year-old person. To the 30-year-old person, I give the treatment, and I see he recovered. And for 60-year-old person, I don't see the treatment, and I see he didn't recover. Now I'm going to compare it, but then immediately rises a question. Maybe 30-year-old person recovered just because he's young, because they are not comparable. And by matching, we make the subjects that we're comparing comparable. So we'll take a 30-year-old person and who got the treatment, and another 30-year-old person who didn't get the treatment. And we'll compare them. And now we have more, rights to conclude that this treatment worked, because at least the age didn't matter. There might be other things, like, for example, the health condition, or what else? Yeah, essentially health condition, or in the environment in which you work. But you essentially try to control for all possible things that can have an impact, so that your comparison will be valid. I hope this answers your question. Do you use Euclidean or Mahalanobis distance on 33? This is not Euclidean distance. This is the other one, as you said. But I took this example from. Do I cite it here? From the course that is definitely cited somewhere in the presentation. So I didn't compute the values, I took them, but they were already, yes, they used the second, not the Euclidean distance, but Mahalanobis distance. Next question, slide 45. In the modeling following digital twin approach that nowadays seems to be implemented in all fields, and how machine learning can increase the evolution of digital twins. Slide 45. Okay, so about digital twins, I might not be in a position to give a good answer because I only heard about this concept, have some understanding, but I didn't work with it. But yes, of course, yeah, from my understanding of what digital twins are, definitely this is the same idea. How can machine learning increase the evolution of digital twins? Well, we can definitely, if the digital twins are properly done and have all all the causal connections are properly represented, then definitely we can use machine learning on this. For example, digital twins that represent hypothetical situations. And we use the standard machine learning models, and we don't need to have any additional assumptions because we already have assumptions about the model. To conclude some causal relationships as well. Hope that answers your question. How does your approach on slide 47-49 deal with two-way effects, price versus demand? This is which approach? So you mean that X causes Y and Y causes X? If it is the question, if not, please reformulate it. But in this case, we assume, as we said, that we are working with graphs without cycles, and we assume that there is only one direction of the relationship. There is only one variable causes the other, and the question is is it possible to distinguish just using the data set and these assumptions, in particular that the noise is additive, between the direction of the relationship? And it turned out that yes, in some cases it is possible. Definitely, yes, I will share the slides. And the last apparently question, if there are unmeasured confounders, you might not be able to block the backdoor path, right? Exactly, correct, because you are not able to control for these confounders, so there is no way, but that's why instrumental variable analysis can be interesting, because essentially it allows us to forget about the unmeasured confounders. We don't care about them, we are trying to evaluate causal relationship through a different path. Or for example, even regression discontinuity, the same. From our assumption, we assume that these people just after the cutoff and just before, they are the same. So it is not mandatory for us to think all the possible characteristics in which they are the same. Like in this case, it will be like just their ability is the same, but how is this ability represented and how control for it? Like we cannot control for ability, but just from the way the design is made, we can assume that in terms of their ability, there is no difference. So we don't have to care about unmeasured confounders because we have sort of baseline, like a foundation to say that whichever confounders can come into picture for this particular problem, they should be the same because they are too close to each other. Okay, hope this answers your question. Thank you very much for your attention. It was a pleasure to present to you today. I think that's all. Alina, should we disconnect?
Yes, thank you.
Thank you very much. Bye.
Bye-bye.